Now we're good? Yeah, without the card, there's just not much point in it. Okay, so let's talk about a couple of things. And if you look on problem 28, because 28 is kind of a nice contrast about what's happening here. So if you look on number 28, so you got an FM radio station broadcast at a frequency 101.3 hertz. What is the wavelength? So you have 101.3. And this is MHZ. So this is where I said you have to begin to look at, we're going to get into some really weird kind of like prefixes for numbers. So if you look on that M, that's mega, which is 10 to the 6th, okay? So that's like a pretty high frequency, right? 10 to the 6th. So what you want to find out is what's going to be that wavelength. So, and here's a common misconception, and I want to get this straight right now. When you're talking about radio waves, even though it's transmitting music, okay, is a form of electromagnetic radiation, okay? It is, do not use the speed of sound for a radio wave. When you turn on the radio, they're not broadcasting sound to your car, okay? They're transmitting photons, and those photons hit the antenna, it vibrates. Your radio then has the capacity to take those random vibrations and transmit it into sound, okay? If you listen to rap music, that's just a waste of electrons, but that's just me. It's like the old joke, you want to make me scream, play rap music. Even that's an oxymoron, rap music, it's not that. So.
Rap sound.
Yeah, rap noise, how about that? And that's even being disrespectful to noise. So, on 28, you should get a wavelength on 28A of 3 meters. Okay, take the speed of sound, do that conversion from megahertz into hertz, okay, 3 meters. So, that wavelength, that visually, for this wavelength, would be like from here, 1, 2, 3, over here. So that's a wavelength of radio. Now, if you compare that to like visible light, okay, visible light has a wavelength like 10 to the negative 6. It's extremely, relative to that, it's extremely short, okay? So this is the cool thing about the electromagnetic spectrum, is that you have these, more so than about anything that you study in science, you talk about a difference of extremes. You have wavelengths of like, 3 meters up to 20 meters. Then the other side of it, you have like X-rays and gamma rays where you have like 10 to the negative 12 meters, okay? So this has more of a gap between the extremely small and the extremely large than about anything else you're going to study in science. But then also correspondingly, you have a huge gap and difference in the frequencies, and you have a huge difference then in the energies, okay? So the advantage of radio waves is because they have such a long wavelength, they're not distorted very easily by dust, clouds, that type of thing, okay? So this is why we use radio waves and we use that wavelength and that frequency when we're trying to communicate with probes that are outside of our atmosphere, because we can transmit them and receive them without them being distorted by our atmosphere. Now, our atmosphere is kind of cool for any number of reasons. Number one, it lets through visible light. If we have an atmosphere that absorbed the visible spectrum, we would always be in darkness. Because if our atmosphere did not let in this visible light that we see, the sun would still be emitting energy, but we would never see it. If our atmosphere was opaque to visible light, we would not be able to see, okay? Because if that's what our atmosphere was composed of. Thank God it's not, okay? Thank God it lets in. But the other thing cool about our atmosphere is that it blocks out a lot of stuff. It blocks out a lot of the UV light. It blocks out a lot of the infrared. So if you look at the big telescope that they launched, it was about, on Christmas, okay? That satellite works in the infrared. That's why it can't be a land or Earth-based satellite or telescope, because the infrared radiation that we get from stars doesn't make it through our atmosphere. That's why we had to launch it and get it outside of our atmosphere, which we'll talk more about later. Okay, so then on 28B, then it says, what is the frequency of a sound source that produces the same wavelength in 20-degree air? So what's going to happen then on 28B, now you're going to be talking about sound. So it's a crossover between light and sound. So on B, that answer, you're going to take the speed of sound divided by that wavelength, you get like 120 hertz. Okay? So your answer to 28A is like 3 meters. The answer to 28B, 120 hertz. Now, on 29A, and this is, I think, what Justin was referring to, how much energy is delivered to your eardrum each second? Okay? So what you want to do here is that on 29, intensity is power divided by area. So what you're trying to find is the power. Oh, power is intensity times area. So in this one, because you're talking about the eardrum, okay, you need to find the area of that eardrum. But if you look at what you're given that the diameter of the eardrum is 8.4 millimeters. 8.4 millimeters is about 3/4 of the width of your pinky. Okay, so that's about the diameter of your eardrum. Assuming that it's round, okay, you can find the cross-sectional area of that surface, you can find the area. So because that you're going to use pi r squared, because it's just the area of that eardrum. Okay, so you can go from there. When you get to 30, rock concert, they give you 1 meter in front, da-da-da-da-da. So on 30, you kind of got to do a couple of different things. You need to find the intensity at a distance 1 meter away, and then you use that then to calculate the energy that you're going to receive. So on 30, that answer should be something times 10 to the -9th joules. Okay? Which isn't very much, but it's also your eardrum. Okay? So you got to find that new intensity, so you got to use like that I2 equals that intensity times that ratio of R1 squared over R2 squared. You got to use that. You got to find the new intensity, use that in that power equation. So there you go. On 32 is a cool question in terms of concept, right?
I just assumed
So sun emits electromagnetic radiation, and 4.0 times 10 to the 26th watts. So that's joules per second. Okay, so the sun is cranking out a lot of energy. And it's been doing it for about 5 billion years. Okay, we've got about another 5 billion years to go, give or take about, 10 minutes. That's about how much longer we have. Don't sit there and go, oh my God, the sun's going to run out of fuel. And the sun is. Our Earth, if you really want to have a doomsday thing, our Earth is doomed. Okay, we're not going to last forever. We're not. Okay, is it anything we're going to have to worry about? No. Okay, it's going to happen billions of years. We're going to screw this thing up long before then. Okay, but the sun is going to run out of fuel. It's just going to happen, and then it's going to expand, and eventually it's going to encompass Mercury, and then Venus, and eventually the Earth. Okay, bad things are going to happen, and actually it was, if you look at even that impact on literature, where once scientists, this was like in the 1800s, once they figured out kind of like this whole concept of entropy and what's going to happen in the universe, it actually kind of like even impacted literature in Britain and England and France, because they realized it was kind of like this doomsday thing. It's like, we're screwed, and it literally, like, everything kind of took like this weird kind of downward turn. It was like, well, hell, we're screwed. What's the point?
Sun also.
And then they realized it was a long way out, and they go, okay, we're okay again. And they invented heroin and life. Okay, so it's a true story. It used to be that you could buy cocaine like over the counter, like in the late 1800s, early 1900s. you could buy cocaine. It was a pain medication. You could buy it over the counter. Okay, it literally, you could go up to the counter, buy cocaine. You used to be able to do that. Okay. Now, so let's talk what's going to happen on 32. So on 32, you want to figure out the energy that you're going to get, and that's why I said you got to refer to that table of astronomical data. And you want to determine the intensity of the electromagnetic rays from the sun just outside the atmosphere of Venus, Mars, and Saturn. So basically what you're going to do is that you're going to use that intensity, use 4 pi r squared, okay? So you've got that same power. The only thing you're going to divide by is, the only thing that's going to change is that radius. Now, let's say that I gave you I didn't, but let's say I asked you to draw a graph of intensity, and here's the sun, and here's the distance from the sun. What would that graph look like?
Inverse. Sorry.
Something like this, right? Okay, that's the whole point. So this is why everybody says, oh, we'll use solar power to generate electricity for space probes. And as long as you're even kind of Mercury, certainly that's close. Oh, we can do that. I was getting a lot of intense sunlight. Get out to Mars, quite a bit weaker, okay? You get out to Saturn, Jupiter, things like that. The amount of sunlight that you get per square meter is so small that you're not going to generate very much. Whoa. That scared me. It's like I was in the zone, man.
My bad.
It's okay. What fell? Oh, okay, gravity storm? Man, that sucks. Okay, so that's why when you get probes that are like the Cassini mission, they actually used a small radioactive reaction, basically. It was a nuclear reaction and a radioactive source to generate electricity, because they knew they couldn't get enough electricity from the sun, solar panels, to generate enough electricity to run that. So what you should see is that on Venus you should have a watts per square meter of about 2,700, and then it's going to go down to Saturn all the way down to like something close to your age. So
600?
that's a pretty big drop, okay? That's a pretty big drop. What?
I was like 600 is not close to my age.
No, the Saturn one.
Okay.
Yeah, the Saturn. Big difference. Now, when you get to 34, okay, because 34 is kind of a near and dear question to my heart, in case you can't tell. I really like 34. And so, and in all honesty, most like the solar cells that we've got are actually about 20% efficient. So basically and this is the cool calculation on 34. Is that okay, well how big a solar array would you need to power your house? So the whole key to this is that you're only about 15% efficient. So you're going to need more energy than what you end up with, because you're only able to convert about 15% of it. Okay? So out of the 100 units of electricity that hit the solar array, you're only going to functionally be able to get 15 out of that. So you're going to need more than what you need to end up with what the functional part. So basically, take the 11,000, divide that by 0.15, that's how much you're going to need. You know how much energy you can get, watts per square meter, that tells you the area that you're going to have, okay? Which is about 370 square meters. Okay, so your answer to 34 should be about 370 square meters. So to give you some perspective, if you consider that, if that's 370 square meters, right? So if you have like a football field, so a football field would be 100 meters long, okay, about 100 yards, right? So that means that would need to be 3.7 meters wide, okay? So 3.7 is about from that wall over to here. So if you consider like a football field length, and that's about how long these arrays are out here. Each one is about a football field length, and that's about, there's like 3 sets of arrays. This is about the dimension of each one of those. So that's how much you would need if you were to getting all of your electricity just from the sun. Obviously, that changes throughout the year. In the daytime, in the wintertime, you're not going to get as much sunlight. The sun is lower on the horizon. In the summertime, the sun is higher. You're going to get more direct sunlight coming down. Your efficiency actually goes up. So there's a whole bunch of variables that play into that. But a lot of people says, oh, we can use solar power. Well, you could, but most people don't have like a football field length area to generate that much electricity. You can produce a lot of it, but you probably don't have just enough surface area to produce all of that. Now, but from a production standpoint, what could you do to reduce that area?
Stacking.
Increase the efficiency. So if your efficiency goes up to say 20%, oh, okay, now you're not going to need as much surface area. So then that becomes more viable. And that's kind of where everybody's going right now, is trying to improve the efficiency. They're also coming up with some new materials. It's like these rays, this solar array down here is a silicon-based array. Each one's pretty heavy. Well, that's one of them right there in the back. Okay, that's just one of those panels right there, and they're pretty heavy. But now they're coming up with really, really thin, like basically like about the thickness of maybe like a piece of paper. And so if that's the situation, then it becomes, you can put them on a lot more surface areas because you don't have that weight load because of the fact that the material itself is so much thinner. So I think in your lifetime you're going to see some pretty cool things happen.
Why don't
with
just
that.
make human
Okay.
double wheels attached
So-
to like kinetic generators, you know? And then you just have like a group of slaves rotate in and out of who's on the human gerbil wheel, just making electricity. Well, you could like feed them or pay them or something. They're not slaves, they're
Indigenous servants.
But yeah, you just have them rotate like every 3 hours. Walking on
The speed at which they would have to do to generate any kind of like.
What do you mean? You
real-
can definitely
but,
do
like-
some gear ratio magic and.
But then you need a lot of torque to get it started.
Okay,
in the
well,
first place.
have some bigger slaves. Laborers. You gotta be at least 250 pounds.
Oh.
Yes.
There's Clady.
So now I put the batteries aside. So what this is showing is the decibels, right? So if I'm not talking, you've kind of got this background noise level of, hold on. Around 7. So, but if I begin to talk into this thing, and now I'm up to like 100, 95, stuff like this. So this is a logarithmic scale, okay? Because it's a log-based 10. So if I really, really scream into this thing, okay? So you ready?
127.
Which just wrecked my throat. What did it go up to?
120.
120?
Mr. Bergkamp, where do you want this to be focused at?
Huh?
Do you want?
Just here in this whole area,
All right.
okay? So it went up to about 120, so we'll try this again. Ah! Yeah, not bad, okay?
I could do better.
Now, if I do that and I hold this further away and I yell at that same intensity, what's going to happen?
It's gonna decrease the decibel.
Ah! So now when I do it, only went up to like what?
106.
106. So I was still producing the same amount of energy, but because that microphone was further away, guess what? That sound intensity dropped. And if I held this all the way, here, Mom, that way over there, okay? So if I do this, okay, and now I yell, ah!
93.
Yeah, you get like 93. So that's that whole idea of dividing by R squared. So when I was really, really close, we were up around 120. Bond holds it over there, that's going to drop like a rock because of that inverse square. So when you all go to concerts, and you know you're probably going to, and everybody's going, oh, let's go up by the stage. Remember this demo, okay? Remember this demo thing. Oh, that's my energy. Everybody's going, nerd! Yes, but I'm going to have my hearing, okay? So,
Nerd.
I'm just saying. All right. So on 38, that's just a straight calculation. So that answer to 38 should unfortunately be something close to my age, about more than that.
600.
But shut up.
Oh, my bad. E to the negative first.
So your answer to 38 should be between 60 and 70. Okay? On 48, 48 is more of an algebra problem than anything. So on 48, that's what we talked about yesterday with the osprey. Okay? So if all goes well on 48, that velocity should be between 10 and 20 meters per second.
I don't feel like it's very fast for a bird falling.
15 meters per second?
Yeah, no, I don't think that's very
It's
fast.
faster than a human can run.
It's less than 90 kilometers an hour.
Yeah.
So
Well, I didn't say it was top speed, you know.
it was in a
All you're
gentle
figuring out
dive.
is-
That's not
Yeah, it
Do you
doesn't
realize
say
how much 15 meters are?
diving at you. It doesn't. All it says is diving. It doesn't say it's like
Birds
a
in New
straight
York
blue
go like
bolt.
250 miles an
Back
hour.
off, okay? This is what you get. God, this isn't biology.
underestimating
all right?
11 meters per second.
I'm not
Anyway.
as
Small meter.
slow bird.
So there's that. Okay. Any questions on the rest of it?
39.
I don't even know how I calculated that. I just magicked an answer.
Okay. Problem 39? Seriously?
I think that was pretty easy, actually. Simple.
Okay.
Simple, 969.
So on 39, you know I2 equals I1
I wasn't doing that.
R1 squared over R2 squared. Okay? So on 39, you've got, what's the sound intensity of a whisper at a distance of 2 meters and watts per square meter? So the whole key to this one on 39 is that you have to start with that initial intensity. So on 39, you have a whisper, right? So if you go to here, on page, whatever page that is, there's a chart. Nope, wrong one. Sound.
Oh my goodness. Oh my Lord, good Lord. 2 meters, right? 2 meters. One is unimportant.
So it's got the whisper on page 486. The intensity of a whisper is 1.0 times 10 to the negative 10. So that's what you're going to use for that I1, and then it's just a ratio of your distances. So without that number, you can't do it. So that's the whole key to 39 is finding what that intensity is at 1 meter.
You just flip
But then you're going to go to 4 meters. So is your answer to
the BD.
at 2 meters going to be bigger or smaller than what it is at 1 meter?
Small.
Smaller. So you know your answer has to be smaller. And if you think about it, you're going to double the distance, but it's a squared function. So it's going to divide by 4. Just the short version is that you take that intensity at 1 meter and you divide it by 4, and there's your intensity at 2 meters. That's the simplest way to go. Okay?
10.
Yeah, without that number, you can't do 39. Okay, anything else? Evan?
Can you go over like what we should get for certain answers on like 31?
Something times 10 to the 5th.
What should we get for
Seems even louder. I don't know much about sound though. No.
sound good?
Looks
You're good?
like standard talk.
Yeah.
Okay. Anything else? Going once, going twice? So get that handed in.
Pause it.
Huh?
I guess he wasn't ready.
Okay, so when you look at intersections of waves, and this is like the old school like way of teaching. And so what I've done is I've drawn like 2 different random waves on this. Okay, that's that one. They're kind of the same. So what happens when you have an intersections of waves? You can have 2 different types of interference. One is what you call constructive interference, where they reinforce each other, and then you have destructive interference, where they cancel each other out. Okay? So in one situation, they're going to amplify each other. The next situation, they're going to cancel each other out. So if you look at what's happening, so I've got, imagine that I have this wave traveling in this direction, and I have this wave traveling in the opposite direction. So if you go to like an extreme, and if you get a situation like this, where they're exactly like this, so what would happen?
I don't understand.
So what would happen here is that you have this wave up here, you have this wave down here. So it's like an additive property. So what's going to happen is that these would actually cancel each other out. So this would be a classic example of what we call destructive interference. So the energy of this one on the top poles is just going to cancel out the energy in the bottom poles, okay? And what would happen is that if this would sound like whatever, what would happen is they would cancel each other out because this is destructive interference. Now, the other thing that you can have is what you call constructive interference. So if you had constructive interference, where they would be on this, where they would be like in phase, where they're both down here like this, this is what we call constructive interference. And what would happen is that this would actually become much deeper because it's like adding these 2 waves together. So in one extreme, you have constructive interference, where they're going to amplify each other, and this would become much deeper. If you have destructive interference, then they're going to cancel each other out like this. That energy is like one's trying to make it go one way, the other one's going to make it go the other way, and it's going to cancel out. So we're going to try and show that on the spring. So we're going to need the camera and the back. So just unplug it from the power source. They don't have a battery light.
Let's go.
All right, Paige, I'm going to need your help.
Dude, look, it's little tiny Kyle.
Hey, Kyle.
Tiny Kyle.
Hey, Kyle.
Show your butt.
Imagine.
Full cheeks.
Now, yeah,
Cheeks.
Okay.
Oh.
So, if you just have one wave like this, right?
Kind of wild,
So,
Kyle.
you can only have constructive and destructive interference when you have waves going in opposite directions. So, one single wave
It's all
can't
right.
like interfere with itself. So, here's what we're going to do. Okay, this is going to be a timing thing, okay? So we're going to try and do constructive interference first. So what's going to happen, I'm going to count down. I'm going to go 3, 2, 1, and then I'm going to send a signal like this, and I want you to send a signal in that same way towards me, okay? So we're going to go, yep, so we're going to go 3, 2, 1, and then I'm going to do this. Ready? So 3, 2, 1. Now, if you notice what's happening on that one, I'm sending a wave on this side. Now, I'm not going to do, you do yours, what you just did. So she's sending a wave on the opposite side. So in that situation, that would be destructive interference because that wave is coming down on her side, on her right side. Mine is coming down on my right side, and they're going to cancel each other out. If we want constructive interference, then we're both going to go in the same direction, okay? So let's try that one. So you're going to do yours the opposite of what you just did on that one. Okay, you ready? 3, 2, 1. Now try it, make it go The other way. There you go, like that. That's what you want to do.
Okay.
Okay, you ready? 3, 2, 1. Now, if you notice that one, let's do that again. 3, 2, 1. So with that one, notice that a couple of things happen. The energy still transfers through. So what's happening in that brief intersection, when those waves are connecting and they're in the same place at the same time, they're trying to amplify each other. So when those waves are interacting, it's going to do one of two things. They're either going to try and cancel each other out if they're on opposite sides, or they're going to amplify each other and make that bigger. Okay, so either your amplitude gets smaller or your amplitude gets bigger depending upon the situation. Got it? Okay, well done. Now for the challenge. So here's the anomaly of sound. Sound is a compression wave, but when we're going to draw this, we're going to draw it like a longitudinal wave. Okay? So, mainly because it makes the visualization easier to see. So, and this is the lab that you all will do tomorrow. So, I'm going to take this, okay, and I'm going to hold this over the top of it. So what's happening is that there's water in this tube, and you have like a surface of the water inside. So what's happening is that when I do this, it's sending a vibration down the tube, it's hitting the surface of the water, and then it's bouncing back up. So that's like Paige and I sending waves at the same time, okay? So you have a wave coming down, it's hitting the water, and then it's bouncing back up. So, but as it bounces up, it's running into another wave that's on its way down. So one of two things are going to happen. It's either going to kind of cancel it out, or it's going to amplify it, and it's going to make it louder. So when we do this, now, so if I lift this up, what you'll find see how that got louder? I got so much background noise going on.
Science is
That could be
broken.
my shoe. Let me try a shoe.
I think you just do
No.
a game clean, super loud ring, but you deform the force.
There you go, that's a good one. Okay,
That's impressive.
so with this one, okay, you hear that point where it gets really loud?
It gets louder.
At one point right there?
Is that the construction zone?
So what's happening, where it reached that point where it got really, really loud, that's like a classic example of constructive interference. So what's happening is that that sound wave is bouncing down. It's in phase with the sound wave that's bouncing back up. And then when that hits, and they're like amplifying that. So as that gets amplified at that one point where everything is in phase, that's when that sound got really, really loud. Okay? So that's just kind of a way to hear what's taking place. So when you're going to draw, and this is you're going to have to do something simple on your assignment. When you have these waves, so visualize this. You have these waves going along. So at this point here, what would happen is that these would basically be canceling each other out. So when you're drawing a superposition of waves, think of adding these together. Oh, if I were to like, this would pretty much cancel each other out and you wouldn't have nothing. So even though these are waves, at this point when you're drawing this, you would have nothing here because it's going to cancel each other out. So you would still have this part, you would still have this part. But in the middle, that's going to cancel each other out. So then, as they go past each other, then what's going to happen when you get like this, okay? Now, once you get to this point, oh, now these are going to be in phase. So this now would become much bigger here, and this would become much bigger down here. Because now they're in phase, and now they're going to reinforce each other, and you're going to have constructive interference. So, constructive interference, they're going to amplify each other, and if it's talking sound, it's going to get loud. If you're talking light, it's going to get really bright, it's going to be more intense. If you have destructive interference, like the noise canceling headphones, okay, you're basically, what's happening is that they're out of phase, they're going to cancel each other out, and you're not going to have anything. The energy is still there, but that energy is canceling each other out. Okay. So, yeah, that's old school right there. Okay. Okay. I knew I had that pin somewhere. This diagram will make sense in just a second. Okay, so if you remember back when we first started this, and I was vibrating and Paige was holding it, okay, we were setting up different wavelengths, okay? So one of the simplest ones that you could have is where you set up an entire wavelength in this system. So I'm here, Paige is here. That would be the difference, that would be the distance between the two of us. And if you have a situation like this distance between the two of us is going to represent the wavelength, because that's what you have. You have one complete length. Now, in this situation, the length, and we're starting with something simple. Oh, here's a good visual. Length equals the wavelength. Now, you have terminology. You have nodes and you have antinodes. So nodes are the points on the string where it's basically not moving. Your antinodes, oh, that hurt. Your antinodes are where you have maximum displacement, okay? So if you think about this in terms of like a velocity time graph, this is going to be like this amplitude. So this is why we studied oscillations before we studied sound. So if you look at this, this is going to be traveling fastest in the middle. It's going to be at 0 on either ends. Oh, it's going to be accelerating. Oh, the velocity is always changing. Oh, that's going to require a force to make this thing vibrate. So if this is a situation, the length equals your wavelength. That's as simple as it gets. Now, if you back up a little bit, what we did the very first time is that we had Kristen, you were counting this one. You were timing, Kristen was counting. So the very first one we did was the simplest one, where I just had it like going back and forth like this. Now, if you think about this one, this here, this distance is half the wavelength, because at any given point, you're here, and you kind of have to use your imagination and go, oh, right. The other part of that wavelength is going to be over here. So if the distance between Paige and I was, let's say, 2 meters, just make up a number. If this is the situation, if the distance between page and I is 2 meters, what's the wavelength going to be? 4, so it would be twice that. In this situation, the wavelength is just going to be 2 meters because that's just a standing wave in between page and I. So you can get more and more complicated, right? So if I did one like this, so if you had this, and that gap between page and I is still 2 meters, what would the wavelength of that be? 1. Because if you look at it, oh, there's one wave. Oh, there's the other one. So in this situation, the wavelength would be 1 meter. So this one, the wavelength is 4 meters. This one, the wavelength is 1 meter. That one, the wavelength was 2 meters. So look at this. As the number of nodes and antinodes increases, what happens to the wavelength? It decreases. It becomes a smaller and smaller number. Okay? So as you put more and more waves in there, you increase the wavelength. Or excuse me, you decrease the wavelength. But what's going to happen to the frequency? Frequency is going to go up because you're going to have more and more vibrations per second, and that's going to take more and more energy. Okay. So, let me see, we got that. Okay. So when you look at tubes, actually, I forgot to get one thing. Stop that for a second. I forgot to get. Okay. So start that back up. So one of the things you can do to demonstrate the Doppler effect. If I swing that around over my head, can you hear the difference in that? Okay? So as it goes towards you, that wavelength is getting compressed, and as that wavelength gets compressed, you hear a higher frequency. As it goes away from you, it's getting stretched out, the wavelength is becoming longer, and as that then that's going to shift that frequency. So as this goes around, now I don't hear any difference. Why do I not hear any difference?
The distance is staying the same.
Yeah, it's always the same distance for me. Now, so this is what's known as, so this system where I did with the tube, actually it's right there. So this is an open, closed system because it's open at the top, it's hitting the water, and it's bouncing back. Now this one is called an open system. So with this one, it's the same idea, but if we can hit that point of resonance, then it's going to vibrate, it's going to make that air inside of it vibrate, but it isn't necessarily going to bounce off, it's just going to begin to vibrate, but it's going to be based upon a certain wavelength. So if I do this one, I hold that up. Now if I take that away, it stops. But if I do it with this one, now I take it away, you can still hear it. Because what's happening is that on that wavelength, it makes that column vibrate, but it's at that resonant frequency and that resonant wavelength where it still continues to reinforce itself. But, so that's at 880. This is 883. So there's only a difference in frequency of like, that's 880, this is 883. Well, with this one, okay, you can hear it, but as soon as I take it away, it stops. Because there's enough of a difference in that wavelength that it doesn't hit that resonant frequency. But if you do it at 880, then it'll continue to vibrate. Okay? And so that's the importance of how length influences that system. So when you have, and then this is where we use the, admittedly the wrong mathematical model, but it works, okay? So when you have an open, closed system, okay, and this is what you're gonna do in the lab tomorrow. So you're gonna have a tube, and it's going to hit a solid bottom, and this is going to be open at the top. So hence the term an open closed system. So here's the best visual that we have. We're actually going to use a transverse wave to represent a longitudinal wave. So let me kind of draw this down here a little bit more where I have some room. I got to tap into my inner artist here. That's not too bad. Just wanna make sure I got that dry right. Go away. Okay, so when you have an open-closed system, so when I did this and held this on here, okay, when we have that point where it gets really, really loud, and we have that constructive interference, mathematically, here's the easiest way to look at this. What you'll see is that even though it's a compression wave, we're going to represent it as a transverse wave. So when you have an open closed system, imagine that what you're seeing is 1/4 of the entire wavelength. So what's happening is that it's coming down, it's hitting the surface, and it's bouncing back up. So we're reinforcing 1/4 of that wavelength. So what you're going to do in the lab tomorrow is that we're going to measure this distance. Okay, so you're going to do this. You're going to do exactly what I just did tomorrow. You're going to adjust that tube until it gets really loud. And then what you're going to do is you're going to measure that distance. So once you measure this distance, then to find the wavelength, you're going to multiply this distance, oddly enough, by 4, and then that's going to give you the wavelength of the sound. So this is a cool way that we can measure a wavelength without measuring the wavelength, okay? So if we can figure out what that distance is, we multiply that by 4, oh, there's the wavelength of the sound. Because it isn't something like we can see, it isn't like, oh, I'm gonna hit this tuning fork and then you all can look and go, oh yeah, here, I'll hold up a meter stick and I'll measure the wavelength, okay? You can't do it. But if we can measure the distance to where it becomes reinforced, multiply that by 4, there's the wavelength. Then, like in this one, I know that this is a, what is it? A 523.2 frequency. So if I know the frequency of the tuning fork, and I know the wavelength of the sound, if I multiply those two together, what can I get? Velocity, which should be the speed of sound. So what I can do is, with that, a simple way is, hey, what's an estimation of the speed of sound? Oh, figure out what the wavelength is, you know what the frequency is, multiply those two together, hey, voila, you get an estimation of the speed of sound. So that's what you're going to do in the lab tomorrow. Now, if it's an open system, that's a little bit more complicated. And you also don't get as like strong of resonance. So on an open system, as the name implies, so what's happening here So on an open system, forgive the crudeness of my drawing. So if you look at this, you're here, and it's coming down like this. So what portion of the wavelength is this?
1/2.
Half. So on an open-closed system, that point of resonance comes at 1/4 of the wavelength. If it's an open system, your resonance comes at half the wavelength.
Is this always?
So if you know this length on an open system, how are you going to find the actual wavelength?
Multiply by 2.
Multiply by 2. So what are you going to do tomorrow? And I'll tell you, and open ones are notoriously difficult. They're harder to hear. So with this one, so what you're going to have is you're going to have two pipes like this. So I'm just going to try. I'm going to try and do this. It's going to be hard to hear, but so especially when I'm going to try and do this all at one time. So you're going to do this. You're going to hold it on one end. And then you're going to adjust that length. That actually wasn't bad right there. So that got louder. And not as loud there. That's actually not bad. That worked better than I thought it was going to. I wasn't surprised. So on an open system, then you're going to listen to that. You're going to find that point of resonance. And then you're going to measure this length. So then when you get this length, then how are you going to find the wavelength? No.
Multiply by 2.
That distance represents half the wavelength. So to actually get the wavelength, you're going to multiply by 2. Then, if you know the frequency, then you multiply that together, you get the speed of sound. So here's what you need to remember. If it's an open-closed system, that point of resonance is at 1/4. Now, you can actually, and it's really, really faint. You can actually hit another point of resonance if you lift up high enough, where it will actually happen at 3/4. So you can get it at 1/4, you can actually get it at 3/4. So if I do this, okay, so there's that first one. If I go high enough up, right there. That got a little bit louder. So that would be 3/4 of the wavelength. So it's going to happen at 1/4, and then it's going to happen again at 3/4. But the 3/4 one's harder to hear because it has such a massive column of air that you're trying to vibrate. So it's really, you don't get as strong as like a resonance. But that one at 1/4, all day long. 1 at 3/4 is going to happen, but it's not going to be as intense because you have so much air that you're trying to make vibrate. Okay. It's killing me. I think we're good. Now, when you get into a little bit of music terminology, just a little bit.
Yeah, I played violin. Yeah, I didn't really play violin. I hit the strings and the bow.
Okay, so when you have what we call fundamentals, so fundamentals are like multiples of the wavelength. So if you have an open system, your fundamentals occur at every integer. So like 1 wavelength, 2 wavelengths, 3 wavelengths, whatever. On an open closed system, because you're dealing with like 1/4 and 3/4 and things like that, those only occur on odd numbered lengths. So it's 1, 3, 5. So on that first fundamental, m's gonna equal 1. So if you were to find like the next one, then that would be where m would be equal 3 on that third. So open, close goes on odd numbers. If it's an open system, they go on every integer. That'll make sense when you get one of the problems on this assignment. Okay, my voice is about to die out. So I'm going to get the assignment, and it's relatively short. So this is out of chapter 16. And no, I don't know the page number, but I can look it up.
So 1 through 5, or is that negative 1 through 5?
That's just like every that's supposed to be the second line.
I guess I don't get it. So, Mr. Birdcamp,
What?
is the 1/4 rule and 1/2 rule true every single time?
Yes.
All right. So open close is always 1/2, or 1/4.
Yeah, there you go.
That's on 524. Is the page number.
One, 4 through 8. Probably. So what? On the assignment 11, 20, 21A, 22, 26.
So on some of these questions, you're going to need this formula that's in the book. But what it's referring to is the tension on a string. And so that's 2 times the length. So here's what's going to happen. So like if you look at like a banjo, right, or any stringed instrument. So this is this U that we talked about. That's that mass per unit of length. Okay, so that's like a fixed value depending upon the string. There's your tension. This is your frequency. So and this is like the L, which would be the distance that it's going to vibrate, right? Like that comparable to the distance between me and Paige. Okay, that would be that length. It's a fixed value. So if you look at this, so if you do this one, okay. Now, if I increase that tension, what happens to that frequency? It goes higher and higher and higher. So that's what's happening here. So that frequency of that vibration, this is the one that you're going to control on a given stringed instrument. You're going to control that tension. So if you increase that tension, you're going to make that frequency go higher. So this is going to play out in some of these questions on 4 through 8. It's in the book, but assuming that you all aren't going to necessarily, this is going to save you some hassle. That way you don't have to look at that equation. So, okay, I'm done. My voice is killing me. Run. He's got that assignment. I already gave it to him.